In this video, we present the Seldonian Toolkit, which enables software engineers to integrate provably safe and fair machine learning algorithms into their systems. Software systems that use data and machine learning are everywhere, but these systems can produce unsafe and unfair behavior, like suggesting potentially fatal medical treatments, making racist or sexist predictions, or facilitating radicalization and polarization. To reduce these undesirable behaviors, software engineers need the ability to easily integrate machine learning algorithms with domain-specific safety and fairness requirements that users, such as doctors and hiring managers, have the expertise to define. The Seldonian Toolkit provides special machine learning algorithms that enable software engineers to incorporate the user's definitions of safe and fair into their systems. The toolkit contains a graphical user interface that can easily be adapted for many use cases. The engineer can define safety and fairness constraints within this interface, and then can provide a machine learning model that will be trained by the toolkit according to those constraints. The Seldonian Toolkit provides two key contributions. The first is that it is industry agnostic because it provides common definitions of safety and fairness, and it allows the creation of custom definitions. The second is that the toolkit implements a safety or fairness test that reports if it was unable to produce a model that has been verified as safe with high confidence. This separates the toolkit from other libraries, such as IBM's AI Fairness 360, Microsoft's FairLearn, and FairKit-Learn. These libraries are also designed to identify and mitigate unfair behavior, and they are becoming more widely adopted. However, they lack a safety test. In comparison, the Seldonian Toolkit provides a high confidence guarantee that when the system is applied to new data in the field, the safety and fairness constraints will hold. To see how the toolkit can be applied in a real-world problem, let's suppose a software engineer is tasked with building a system that predicts housing prices within 2 zip codes. The engineer has historical data that describes how various features, including zip code, size, and year built, influence housing prices. Here's an example of what that historical data might look like, with the plot depicting the housing prices in both zip codes versus house size. The user has insisted that the system must have similar accuracy in both zip codes, perhaps because these zip codes correlate with the residents' races. If the engineer used a standard machine learning algorithm on this data to predict housing prices, they might obtain a line like this one. However, if we color code the same points by zip code, the same red line that was fit to all points would have worse accuracy on houses in zip code number 2, orange, versus zip code number 1, blue. Using the Seldonian Toolkit, the software engineer specifies the constraint requested by the user, that the accuracy of the line for both zip codes should not differ by more than some value, say 0.2. The toolkit will find a line, shown in green, that is the best possible fit for the data while satisfying the constraint with high confidence. There are trade-offs to applying these constraints. Depending on the dataset and the choice of constraints, the toolkit may sacrifice accuracy. As we can see here, the green line is not as good of a fit to all the points as the red line was. Adding a constraint can also increase the amount of training data and therefore runtime needed to obtain a safe, well-performing model. To convey these trade-offs, we created a component of the toolkit called the Experiments Library, which produces the following 3 visualizations to help engineers make decisions. The first visualization conveys accuracy in terms of mean squared error. The larger the mean squared error, the less accurate the model is in explaining the data. The second visualization shows how much data is required in the training set to produce a model that can satisfy the high confidence safety constraints. The third visualization shows how often the model's solutions violate the constraints when applied to new, unseen data. The model without the constraint, one that could be trained without the Seldonian Toolkit, almost always violates the constraint, whereas the model with the constraint never violates it. This plot shows the power of the safety test and what the other existing libraries lack. The Seldonian Toolkit makes high confidence guarantees that when the system is applied to previously unseen data, it will not violate the safety and fairness constraints. In summary, the Seldonian Toolkit is a set of software tools that allow software engineers to include safe and fair machine learning algorithms in their systems. We hope this makes it easier for people and institutions to apply machine learning responsibly, especially to high-risk applications.